Okay, so let's consider some additional statements. So we've already considered statement G. Now let's consider, which is that the equation AX equals B has at least one solution for each B in Rn. And now we can add statement H, which says that the columns of matrix A span all of Rn, and statement I, which says that the linear transformation that X is mapped to A times X, that's going to be an onto map. That's going to map from Rn onto all of Rn. And these three statements are all equivalent with each other. And we can see this in the following way, that we've already discussed that if this equation AX equals B has at least one solution for every B in Rn, then that's the same thing as saying matrix A spans all of Rn. Since we can find weights for any vector B, we can find weights x1 up to xn to multiply each of the column vectors of A to combine them linearly to get column vector B out on the right side. And vice versa. If A spans Rn, then essentially by definition, this means AX equals B has at least one solution for each B in Rn. And if statement G is true, then that means that this transformation maps onto all of Rn. Since for any B in Rn, we can find some X, some pre-image of this map, which gets mapped onto B. And similarly, this implication goes both ways. So we can see G implies H and G implies I both ways. I implies G. So all three of these statements, they're all basically saying the same thing. So we can add statements H and I to the collection of previous statements that we've proven are equivalent with each other. And we're not finished yet. Let's consider even more statements. So statement D, the equation AX equals 0, the homogeneous equation, has only the trivial solution. We've seen that statement D is equivalent to a number of these other statements. So now, by linking statement D with a couple of additional statements, we can add even more statements to this list of equivalents. So statements G, H, and I are kind of dealing with the non-homogeneous equation and how that relates to the column spanning A and how that relates to this map being onto. And we have very similar connection between looking at the homogeneous equation AX equals 0. If that has only the trivial solution, we've discussed in the past how that this therefore implies that the columns of A form a linear independent set. And if the columns of A form a linearly independent set, that means this equation AX equals 0 has only the trivial solution. So D implies E and E implies D, and we can similarly work F into this discussion where if we think about A as a map, a linear transformation, we've also discussed previously that if this matrix equation AX equals 0 has only the trivial solution if and only if this linear transformation X to AX is a one-to-one map. So statements D, E, and F are all equivalent with each other. We've already seen that statement D is equivalent to statement G, so we can add all of these statements together now. We've got a whole list from A, B, all the way up to K, where all of these statements are equivalent. So let's list them all out on the next slide. Okay, so here is a mouthful. We've already discussed all of these statements from A all the way up to K. I've added one last statement, L, at the bottom, which says that the transpose of A, so remember this superscript of T means transpose. So the transpose of A is an invertible matrix. We're going to add this to the list. So far we've seen that statements A all the way up to K are equivalent. So if any one of these is true, they're all true. If any one of them is false, they're all false. And now we can add one last statement here about transpose matrices. And we have already proven this actually, that if A is an invertible matrix, then we know that the transpose of A is also an invertible matrix. And the reason why, well, if we assume that A is invertible, then I know I have an inverse, and when I multiply on the right by that inverse, we get the identity. And so if these are equal, then the transposes of their matrices must be equal. And taking the transpose of a product, we take the product of the transposes in the reverse order. And so at this point, from this equation up top, I can see that when I multiply the transpose on the left by the transpose of the inverse of A, we get the identity matrix. But I need to show that if I multiply by this same matrix, A inverse transpose, on the right of A transpose, we also get the inverse. So let's take a look at the other direction. So we can start now with the product A inverse times A equals the identity. We take the transpose of that equation, so we get A transpose times A inverse transpose equals the identity matrix. And now we can see that when we multiply on the right by A inverse transpose, we also get the identity. So therefore, the inverse of the transpose of A is equal to the transpose of A inverse. And we've proven this back when we first looked at inverse matrices. So this tells me that statement A implies statement L, and we still need to get an implication that statement L also implies statement A. So we can get that statement L implies statement A because if I take the transpose of A transpose, recall we get matrix A back. So if I assume that A transpose is invertible, then we know by statement L that its transpose, which is the matrix A, is also invertible. So now we've got that A implies L and L implies A. So if A is true, L is true. If L is true, A is true. And therefore, since A is equivalent to all of these other statements, L also is equivalent to all of these other statements. So the equivalence of this list of statements from A all the way down to L, this is what we call the invertible matrix theorem.